Hello everyone. I would like to present our publication applying improved bee-inspired algorithm for the vehicle routing problem. This problem is in the area of swarm intelligence, also known as a group intelligence, and it refers to such phenomena in which the goal is achieved as a result of the interaction of many seemingly unintelligent individuals or agents. Nature-inspired algorithms are computational methods of data processing in which there is causality observed in natural phenomena. Wide spectrum of AI-based algorithms have emerged in the last decades, including artificial bee colony, particle swarm optimization, BAT algorithm, Firefly algorithm, cuckoo search, and many others. These algorithms tend to be global optimizers, using a swarm of multiple interacting agents to generate the search moves in the search space. The principle of operation of the ABC algorithm. In the ABC algorithm, three categories of bees can be distinguished according to their functions. They are observed, scout bees, and working bees, also called active bees. The observer bees are bees awaiting information about the food sources. They can receive information about newly obtained solutions and compare them with the information they already have. If the new are better, then they will be remembered. When an active bee becomes an observant, then one random bee of the currently observing bees becomes active. Scouts are bees who randomly search for newly sources of food. Scout bees are responsible for finding a random solution. When moving between the peaks of the graph, the scout bee remembers the vertices it has visited. If the obtained result is better than the one currently remembered, then the new result is saved. Working bees, also called active bees, are bees that go to the previously discovered food sources. They are also called employees. Active bees look for a solution that is close to the currently remembered solution. If both vertices have proper connections, a new road value is computed. If it is more favorable than the current one, then it is saved. The artificial bee colony algorithms. It is a group of algorithms whose operation is based on mimicking the way of searching for food by bee swarms. Individuals or agents exchange information with one another that points to food-rich places. The higher the amount of identified nectar, the higher the probability of selecting this source. Let xi be equal to xi1, xi2, and so on, and be the ith solutions in the population at the 10th iterations. An employed B randomly selects a different solution xk from the current population and chooses a random dimension index j. Then a new solution vi is obtained by vij equals to xij plus vij, where I is equal to 1, 2, and so on, is randomly chosen from the set of -1 to 1. As seen, the new solutions vi is similar to the parent solution xi, and the differences are only in the j dimensions. If vi is better than xi, xi is updated by vi. This means that bees find better solutions during the current search. However, this search process is slow because the similarities between xi and vi are very large. When employed bees complete the search around the neighborhood for solutions, our solutions will be updated by comparing each pair of xi and vi. Then the selection's probability pi for each xi is defined as the following formulas. The vehicle routing problem is a problem that we use as a benchmark to check if our B algorithm works properly. The vehicle routing problem is a group of optimization problems that seek to answer the questions: what will be the optimal route for a set of fleet of vehicles to serve our customers? Example of VRP variants are VRP with bug holes, VRP with time windows, with pickup and delivery, VRP for vehicle load capacity, VRP with bug holes and time windows, with pickup and delivery and time windows, and also distance capacitated VRP. This slide shows the obtained results. We have a couple of cases of results, each of them with different calculated with different parameters. For instance, in this scenario, we have total number of bees, which is 50, including 15 observing bees, 15 scout bees, 20 active bees, where rejection limit is equal to 5 and number of iterations 200. For these parameters and the VRP parameters stated below, we obtained 10 main results, and here are the results shown in the table. We can see that the best solution is a solution number 2 and number 3, which have a total path length of 131. The worst solutions, or the worst solutions of, within this table, is solution number 1, which is 135. The solution number 4, which is also path length of 135, and solution number 10, 135. They have such a path length going through different points, but still this solution are only slightly worse of 4 units of path length than the best solutions, equal to 131. Verifications of the results in case number 1.2 was that the best solution was the solution number 2 with the path length of 84, and the worst case was number 1 with path length of 87, and in this case also the difference between lengths was only 3 units. So these paths were quite similar from the point of view of the total length, but the paths were also going through different points. Verification of results, case number 2.1. In this case, the parameters changed. There are more bees. There are 100 bees, including 30 observer bees, 40 scout bees, 30 active bees, and the rejection limit equal to 10, number of iterations 300. So we have more bees, more iterations, and in this case, as we can see, we could find the total path length of 131. It was in case number 2 and number 3. These cases are actually the same because the path goes to the same points. Worst solutions within this 10 simulation was simulation number 10 with the path length of 135 length units. So it was quite similar to the best solutions, only 4 units of length longer. Results with case number 2, and in this within this 10 results we have best solution number 2, which the path length of 84, and the worst case solution was number 1 with path length of 87. So as we can see, the path length is quite similar in even in best and worst solutions. It is only 3 units of length. Conclusions are that for long distance roads, it is reasonable to increase the number of agents as well as the iterations of the algorithm. The more the iterations and number of agents, the best chances we will find the proper solutions. The longer the algorithm runtime, then the results are more accurate. With the above assumptions, the possibility of finding the optimal road increases. For shorter distances, if there is only 2, 3, 4 of connections between points to achieve start from start point to the end point, these above assumptions are no longer valid. The increase in the time needed to solve a task can increase significantly by as much as 40%. So we change parameters, but the time goes up 40%. Beyond that, it does not really change. The increase of time and calculation does not really change our results. For the correct solution of the problem, it is necessary to establish an adequate relationship between the algorithm working time and the quality of the results obtained. Increasing the number of iterations, even by several orders of magnitude, will not make a significant difference in the results. The obtained results may differ only by a few percent, but the time needed to find the solutions will increase adequately to the number of iterations. If the optimal solution is obtained during the first iteration, the result of the next iteration will not improve at all. That would be everything. So thank you for your time and attention.